Now, a couple of things that are very notable about a strong acid, strong base titration. This will always, of course, is a strong, so it starts very low in the pH, and it just gradually goes up at first, gradually. And then we're going to get very close to the equivalence point, and at the equivalence point, we get this huge jump like that, and then it levels off again. When you have a strong acid, strong base titration, it usually will have around a pH of 10 unit jump. When we get to the weaks, you're going to notice the contrast. It doesn't jump that much. It'll jump, but not like the strong acid, strong base ones do. This is no surprise to anybody because this was exactly what you looked at in your reading assignment the other day. Anybody have any questions at all about any of that? Now we're going to use this to contrast what happens now with a weak acid titration. Kevin, you got a question? Oh, you know what? Yeah, I had borrowed this graph. It was the weak base strong acid titration, so it would be volume of NaOH. Yep. Yep. So is that all right if I just do that? Put a record in my letter in my file, I guess. I'm sticking with it.
It's going to go into your permanent record.
Maybe, yeah. All right, any questions about that? Just pausing for a moment while if you wanted to copy that or do anything with it, it's there. If we started with a strong base and we're titrating with an acid, it would be exactly the same. It would just start high, go down gradually, and then fall like crazy and then level off. No surprise. We good? Okay, I'm going to go all the way back now. One other thing that we need to just at least note is this. When you have a strong acid, strong base titration, whichever you're titrating, either a strong acid or a strong base, the equivalence point is always 7. Because there's once you're at the equivalence point and you've just neutralized all the acid with the base, neither one of them is in excess, and so there's nothing in there in the solution left that can dictate the pH, and so it's just neutral. That will also be different when you have a weak acid titration. And next we'll take on the weak acid.
Weak acid, strong base?
Yeah. Weak acid with strong base. So that's going to take us pretty much up to the end of the hour. Oh yeah, we have a half hour. We can get through that. Now for this titration that we're going to do, I'm going to go through every data point with you rather than just me doing a couple and letting you take off with the rest of them, because there's a lot more to them. And you'll see when we start going through. We'll have just little regions as we go through that kind of change, going from one region to the next. Ready?
Yeah.
All right, so for our weak acid, strong base titration, just arbitrarily, I chose this acid, HOCl. Any weak acid will do. This one is kind of right in the middle of the weak acid table, so I just chose that one. In the burette would be 0.1 molar NaOH. By the way, these titrations, this is exactly what you're going to be doing when you do the lab next week. We're going to have pH meters out. There will be burettes that have NaOH in them, and you'll add like a milliliter of NaOH. You'll swirl the pH meter in there, get the pH, then add another milliliter of NaOH. Swirl and get the pH, add another. It's great. Sounds like fun. I mean, it'd be tough to wait for it now. Is there what? No colors at all. All the solutions are clear. You can't see anything happening except for the pH change.
Could you at least like add for coloring just so that we have something to look at?
No.
How are you measuring the pH?
With pH meter. We have electronic pH meters that have a digital readout. Yes?
I forgot, when do you differentiate between like using molarity and moles?
Yes, right. When you have to do an ice table and use a K, it has to be in molarity.
When do you use it in moles?
You use moles when when you add a strong or weak, a strong acid or base to a solution. When you add a strong acid or base, then you've got to just work out the stoichiometry with moles.
Isn't that the strong base?
Yes, but
Oh.
we're at the data point where none of the base has been added. Yes. So what we have right here, before we add any sodium hydroxide, we should know what the pH is of the acid solution, HOCl, with nothing added to it. So that's where we have to set. This is just like a chapter 14 problem where you just have a weak acid. It's sitting there. It partially dissociates. We're going to have 0.1 minus X over here, X and X. And sulfur X, that'll give you the hydrogen concentration. Ka equals 3.5 times 10 to the negative 8th. And that's equal to X squared over 0.1 minus X. Because K is so small, definitely allows us to use the 5% rule. And if you will, calculate X, that's the hydrogen concentration, and find the pH from that. And when you get a pH, think about it, does that seem reasonable? What do you get? 4.23 sounds good. Does that seem reasonable? Whether or not the teacher just said it sounded good? You remember the acid, the hydrochloric acid? That started at 0.7. It's a very strong acid. You get a flood of hydrogen ions from that. This is a weak, look at that Ka, it's terrible. It's not a good acid for producing hydrogen ions. So you would expect the pH not to be that low because it's such a weak acid. So anyway, it is right. The pH winds up being, I forgot what you said now, 4.23?
Yeah.
Okay. Okay, so this is like our baseline pH, is what we start with, and then we'll start adding the sodium hydroxide to it and see how the pH changes. Okay, so this part will be the same every time. We have 40 milliliters of 0.1 molar HOCl. And what changes, though, is the amount of sodium hydroxide that gets added to it. Now we're going to start by adding 10 milliliters of 0.1 molar NaOH. We do the same stoichiometry as we did with the strong acid, strong base. It looks like this. How many moles of HOCl have reacted? Or not have reacted, are in this solution. 40 ml of 0.1 molarity gives us 0.004 moles of HOCl. And then the NaOH, how much NaOH have we added? 10 milliliters of 0.1 molarity is 0.001 moles. Now the water over here we don't care about. However, the OCl negative, it will matter. So I'm going to say initially we have 0 of OCl negative. Now, this is the proverbial vicious dog attack that I talk about, where you have a strong acid or base is added. It reacts to completion, and because it goes to completion, that's why we use moles. Jane, you were asking about that earlier. Why do we use, or when do we use moles? When you have a reaction that goes all the way, that's when we're going to use moles and look for the limiting reagent. In this case, it's the hydroxide ion. That goes to 0, and the HOCl goes down by the amount that goes down to 0.003 moles. Now the OCl goes up by the amount that those on the left go down. So it's 0.001 moles of OCl negative is gained. And again, the water I don't care about because it's a liquid. So the hydroxide has neutralized some of the HOCl. We need to know what the pH of this solution is. So that means that we need to set up the equilibrium. And we still now have an HOCl solution, so it is going to dissociate into hydrogen ions and OCl, and we'll have an initial concentration of both, the HOCl and the OCl negative. They're right there. Does this look like a drag? every single data point we have to do this for? You know what? I don't think we do have to do this every data point. Does anybody have any thoughts about how we can make our work a little faster? Yeah, we can use the buffer equation. As long as you have a buffer, do we have a buffer now resulting from this reaction? Yeah, we have a weak acid and its conjugate base both together. So take advantage of any time you have a buffer solution, use the buffer equation. Otherwise, we'd have to figure out what the concentrations of these two things are, do the ice table, you know, it's going to go down by X, up by X. I mean, it's not terrible, and we can do it, but the buffer equation is so much faster. So, just a reminder, buffer equation, pH equals pKa plus log of Ba. Yes. The pKa is the negative log of the Ka of HOCl. So what is the negative log of 3.5 times 10 to the negative 8? Seven point something.
7.9.
No.
7.0.
No.
7.4.
Yeah. It's 7.46. Does a 5 round up? Okay. So 7.46 is the pKa plus
Oh, you were asking for the PKA.
the pKa.
Oh, I should ask.
Plus the log of the base is 0.001 over the acid, which is 0.003. And I'm running myself right out of room on this thing. I don't know if I can squeeze the pH down there or not. All right, so anyway, 7.46 plus the log of 0.001